Hi. The most important part in this chapter is you need to understand why the center of mass matters, why we care about center of mass. The center of mass is defined as this equation, right? So position of center of mass is weighted average of positions of individual particles. So for a system of discrete particles, you can find the center of mass by mass times position, sum of mass times positions of discrete particles divided by the whole mass. For continuous distribution of matter, you can integrate the mass element with respect to each position vector with respect to the mass element and then divided by total mass. This is basically just weighted average of the position of mass element, right? Why do we care about this? The reason is center mass obeys Newton's second law. So following as we learned last time, see net force. If net force means here, net force means external force on the whole system of the particles or whole mass distribution. Okay, we ignore here any internal forces between the particles or the mass elements. If external force works, then the net force is equal to, we can say, the force on each particle, sum of all forces on each particles, right? And this individual force on each particle or each mass element can be expressed as second time derivative of mass times positions, right? Because F equals ma. And if we multiply m and divide it by m here, then and this is what we defined as mass, average, weighted average of mass element position, right? Which is center of mass. The center of mass basically follows this Newton's second law, right? F equals ma. So if external force exert on a system of particles, then we can say that center of mass, external force acts like, all the masses are concentrated on the center of mass position. For example, here, so skiers motion. So each part of the skier's body or ski poles undergo various complex motions, but only one special point, which is center of mass, follows this parabolic trajectory which we learned point masses should go through when uniform gravitational force acts on the point mass. This Newton's second law we can apply to the center of mass, because center of mass follows these relations. All the external force act like it works on the whole mass that is concentrated on the special position, which is center of mass. Center of mass obeys the Newton's law by this relation, and we can define this center of mass acceleration as this term: total momentum of the particle time derivative of total momentum of the particle. So total momentum of the system, particle or mass element, is defined as total mass times center of mass velocity. Okay, center of mass velocity time derivative is the center of mass acceleration, and this center of mass velocity times total mass is by definition is just nothing but mass times each mass times its velocity and sum of whole this term, which is basically sum of all mass elements individual momentum. Okay, so after that we went into detail. See here, so why we care about this center of mass? Because center of mass follows whenever external force exists. The external force acts like on the center of mass, where we can think all the masses are concentrated. It follows that special center of mass point follows Newton's second law with respect to the external force, F equals ma. So how do we find center of mass? We can just follow this definition here. For individual particle system, we can just multiply mass times each position of the mass, and sum of those and divided by total mass. That's how we found the center of mass. And by symmetry, without calculation, we can find x component of the center of mass is 0 because it's symmetric along x direction. And in y direction, you can just use this equation here to find the center of mass. And for continuous matter system, we have to integrate its position with respect to this mass element. And to integrate this term, we need to express dm with respect to dx, we can use to calculate this integration. And by comparing this area, we treat this as rectangle, right? So by comparing this whole area to this small area, which is mass element dm to whole m, area ratio is equal to mass ratio because mass density is uniform in this 2D triangle. So we could evaluate this integral, right? Find x component of the center mass and y component of the center mass from symmetry along this direction. Without calculation, we know it should be 0. And when external force is 0, then total momentum should be conserved because dp dt should be 0, right? F net is equal to dp dt. Here p is total momentum of the system. Total momentum of the system, time derivative should be 0. That means total momentum is conserved. This is very important throughout the general physics 1. One of the most important parts. Conservation of linear momentum. When external force is 0, the system's linear momentum, sum of all the momentum, should be conserved, okay, throughout with respect to time as a function of time. For example, there are 3 billiard balls. Initially, these two billiard balls are at rest, and one billiard ball has some velocity v naught. Then total momentum is m, mass of this billiard ball, times velocity, right? mv naught is the total momentum. This should be conserved because here we ignore any force, frictional force, or if there are no forces acting on these 3 balls, no external force. Internal force exists here, right? While they collide, there should be some internal force acting between the balls, but here we can only consider external balls acting on the whole system, okay? So if there is no, for example, frictional force or gravitational force, any other external force, then in this system consisting of 3 balls, the linear momentum, m, mass times velocity, sum of mass times velocity, should be conserved, okay? Total momentum should be constant as of time. So after they collide, the velocity of each ball will change, but some of this momentum should be conserved, okay? Before and after this collision. This is conservation of momentum. Collisions. We just looked at the problem of the billiard balls collisions, right? Collisions, we treat this in physics as a brief intense interaction between objects, okay? We assume that collision time is very short so that all internal forces of the collisions are so large compared to any other external forces acting on the system during the brief collision time. The time is short, so for example, we ignore during the collisions, we can ignore any other forces, for example, frictional force or gravitational force, and so on during the collisions. So linear momentum should be conserved during these collisions. Total momentum should be constant as a function of time before and after the collision. Okay? There are 2 kinds of collisions, elastic and inelastic collisions. Okay? By definition, elastic collision, internal force should be conservative force. In that case, we know for conservative force, kinetic energy, mechanical energy should be okay. Linear momentum should be always conserved before and after collisions, right? This is basically only when as far as external force is 0, linear momentum should be conserved. For inelastic collisions, the force should be non-conservative, okay? Non-conservative force. So mechanical energy is not conserved. But still, linear momentum should be conserved as long as external force is 0. There is totally inelastic collisions. We call this is what we mean by totally inelastic collision is that colliding objects stick together to form a single composite object after collision. For example, if 2 objects M1, M2 having momentum or velocity, separate velocities, and separated initially, and after collision they stick together and they proceed with one final velocity. This is totally inelastic collision. We can apply linear momentum conservation in this case before and after collision, right? During collisions, because we assume there is no external force acting on these two objects during collisions because the force is non-conservative. Kinetic energy, mechanical energy is not. Therefore, we can set up this equation. m1 v1 plus m2 v2 is total momentum before collision, and after collision they move at a common final velocity vf. So m1 plus m2 vf is the final after collision total momentum should be conserved before and after collision, but the kinetic energy is not here. For elastic collisions, as we said, before collision and after collisions, linear momentum is conserved also, as well as kinetic energy is conserved. So we can set up this equation when initial total momentum, sum of initial momentum should be equal to sum of final momentum, right? And also kinetic energy should be conserved before and after collisions. So assume we know v1, v2, and m1, m2 initial velocity for each particle. Can we find the final after collision, the velocity after collision using these two equations? Actually, these two equations, because this v1 and v2 is a vector, this is actually, for example, in two dimensions, this is two equations. This is one equation, right? Then we have three equations, but we have four unknowns, right? Each component of, we have four unknowns but three equations. So we cannot, in general, this conservation law, linear momentum conservation, kinetic energy conservation in two dimensions does not determine. We cannot determine the outcome of elastic collision. We cannot solve for v1f and v2f using known v1, initial v1 and v2. Okay, but for special case in one-dimensional collision, if we know initial velocity of each object, we can find final velocity of each particle. If this is elastic collision, we have two equations, right, in one dimension. So two unknowns if it's one dimension, right? The two equation, two unknown, we can solve. So we can find the final velocity in this case. Okay? For one-dimensional elastic collisions, initial velocity determines the final velocity. We can solve, right, the equation. This is the answer. This is very important part in this chapter. Using this one-dimensional elastic collision equation, right, linear momentum conservation and kinetic energy conservation, you can find from known initial velocity of each object, you can solve, right, final velocity. So special cases for elastic collisions in one dimension is when m1 has initial velocity but m2 is initially at rest. So v2i is 0. Okay, in this equation, v2i is 0. Here is 0. Then what is v1f, v2f? Okay, so we can apply these equations because we assume v2i is 0. Initially, mass 2 is at rest. So for special cases, m1 is very small compared to m2. Negligible. Then what happens here? m1, we can approximate that m1 is 0, right? And m2, we can skip m2. So then v1 is equal to v1f is equal to minus v1, right? Incident object in that case rebounds with essentially the same velocity but opposite direction, and then v2 is still 0. So object 2 doesn't move. Common sense is we can understand because mass of second object is so large, so it doesn't move. And if their mass is the same, m1 is equal to m2, you can see. So incident object v1f is 0, stops. Incident object stops, and struck object v2f is equal to the initial speed of the incident object. Okay, if you have ever played, for example, like billiard or Newton's cradle, I will show in next slide. You'll probably understand what this means. And what if this incident object has much larger velocity? This is the elephant case, this one, right? Then you can also solve for this here, v1f from this equation. m1, you can take m2 is 0, m1 is not 0, right? m2 is 0, so v1f should be, right, v1i. v2f should be m2 0, m1 not 0, 2, v1. So incident object continues with essentially the same initial velocity, and the struck object moves away with twice that velocity. Hey, these stuff are the very important stuff in this chapter. Okay, so Newton's cradle. think about how this works. How this ball knows, one ball struck here. Only if he release two balls, then two balls will pop up here. How does that happen? Think about this. Okay, thank you.